talk, put your cell phones away, and make sure that you're getting here on time. So I want to introduce Professor Maidenberg. He's in the Chemical Engineering Department. If you can, please give him a warm welcome.
Well, hello everyone. So yeah, my name is Professor Maidenberg. I'm in the Chemical and Biomolecular Engineering Department. While there's a B in the CBE, we mostly focus on chemical engineering. That's the main venue of the department. Just as you were just told, this course is actually great. It's going to gear you up to IT design course, which is the last course you take in this class, in this major. I find this course to be quite good at giving you the skills needed for that course, for the senior course, which is quite intensive on its own. So today I'd like to give you a little bit of a history lesson. So it'll be a little bit, in the beginning, a little bit of some history, social science, and then we'll dive right into the engineering and see why it's important. Chemical engineering is of the 4 traditional engineering disciplines. So we have electrical, chemical, mechanical, and civil. Everything else that exists is sort of like an offshoot of one of those, or a combination of 2 of those, or intersection of those. Chemical engineering is the newest of the 4 by a lot. And it's only about 100 years old, which sounds like a long time, but compared to civil engineering, that's been around since ancient times. So it's very, very new. A lot of things have just been perfected. We're learning them as we go along. There's a lot of exciting and new developments in chemical engineering, and I will show them to you. But before we start, I want to give you a little bit of a history of this and see and kind of show you why it is that we need chemical engineering in the world today. And so we'll start with the Industrial Revolution. So before the Industrial Revolution, there was not much of a need for chemical engineering. And before the Industrial Revolution, people tended to live in smaller communities. That's not to say that there weren't cities. There were cities in places like Europe. But by and large, people were much more rural, and they relied on resources that they had around them. So, you go back, say, 1,000, 2,000 years, everywhere was like that. If you wanted apples and you lived somewhere that didn't have apples, well, you wouldn't have apples unless it was an exotic thing that you could see. People didn't have bananas everywhere. People didn't have pineapples everywhere. It wasn't so readily available. There were a lot of things that we have comfort foods or comfort products that just didn't exist back then, because whatever you needed had to be produced locally. So typically what would be done is you would have your own farm and you would grow whatever you needed for your family. And if there was some surplus, maybe you would share it with the rest of the city or the rest of the town, or maybe you'd sell it to some other towns around, where you have some storage for later during years that have droughts or anything like that. As we advanced, we kind of moved away from that model. And now if you brought someone from 2,000 years ago to today, they would not recognize communities anymore. We live in larger communities in big cities like New York City, and where we don't get our own foods, and we don't make our own clothes, and we don't do all these things. And we have to rely on others to do that. And the Industrial Revolution was really the beginning of that kind of transition. Well, not the beginning, but like really the forceful impetus that moved everyone away from that traditional model. And what really we cared about back then is to try to get things that we needed on a large scale. So before the Industrial Revolution, that's around 1700 or so, there were some different things that we needed, what we call commodity chemicals. We still have commodity chemicals, and I'll get back to it in a few minutes. But commodity chemicals like sulfuric acid or potash or ammonia, does anyone know what they're needed for? Like what was that? Yes, fertilizers, yes. So the commonality here, and back then, was fertilizers. Yes, we needed these things so we can grow food. So people would just store them on fields, and it would get more of a yield. So before the Industrial Revolution, it was kind of easier to get because you only needed enough to support your own farm. When the Industrial Revolution came around, and people moved into larger cities, we needed to produce more food to feed other people in those larger cities, and not everyone in large cities would make their own food. So we obviously needed more of these chemicals so we can make more food for a larger community. And what happened was that these are Europeans at this point. What they would do, they would go around the world and they would extract these resources from other countries and other continents, and they would bring it over to Europe so they could grow and become more powerful and have larger empires and all these kind of things. So in the name of empire, people came around and grabbed a bunch of these, and that was the main drive for this empire growth and for colonialism. So that's how that started, and as you can see, before they started importing them, they had some simple chemistry to make this. So if you wanted ammonia, you would take guano and you expose it to hydrogen. Does anyone know what guano is? Yes, it's bat and bird poop. You might have this thing, it's kind of hard to see it, but yes, it is. It is bird poop, and you take bird poop and you just kind of expose it to that, and you get ammonia, which is one of the most important commodity chemicals that we have in the world, and I'll show you that in a few minutes. So this is what we had. In the 1700s, we relied on natural resources. In the 1800s, we started getting depleted because we had larger towns, less people devoting their lives to agriculture, and we needed to make food for all of them. So we needed to go find ways to import them. And in the 1850s, we really needed more. We depleted the natural resources in a lot of areas, and we needed to come up with new and innovative ways to do this. And this is the beginning of the birth of chemical engineering. Well, before I get to that, with the guano, it's a little aside, if you were aware of it or not. The need for guano and for ammonia was so vast that the United States passed a law in the 1800s that any American who sees an island anywhere in the world that is unclaimed can claim it for the United States. And that's how we ended up with a ton of uninhabited islands in the Pacific Ocean. Because these places would be bird sanctuaries, or birds would go there and poop. And so you can extract the guano there and bring it back home, and you sell the ammonia. And so a lot of say like Midway Island in the Pacific, a lot of these large, small, tiny islands had a presence of humans back in the 1800s. Now they're completely desolate. But it's just an interesting aside because it comes directly from this. So this is the person most often credited with the birth of chemical engineering, and George Davis. He started the Society for Chemical Engineers, and really the best way to think about chemical engineering is that it's a combination of mechanical and engineering and chemistry. So up until this point, like I said, we depleted all these resources, and now we needed to come up with new ways to make, say, ammonia. How do we make ammonia? So let's say you have A plus B going to C to make ammonia in a lab. I want to not just make a little bit, because you've all seen labs, there's tiny little areas. I want to make one that's large enough for, say, Brooklyn or for New York City. What do I do? So I need to scale it up. And that's really the name of the game of chemical engineering. I need to scale up this chemistry. Okay? So what they did up until this point is they had a chemist who was aware of the chemistry. Well, if you take A and you mix it with B and you mix it around for whatever, how long, some heat will come out, then you have to make sure that you cool down and do all the chemistry things that you need to take care about. Then you need to purify it and extract things and toss this stuff and all these different things. That's the person who's doing the chemistry. They were aware of the chemistry. Then on the flip side, you have the mechanical engineers who were more aware of scaling things up. Well, great, you're doing it in the lab, how do I scale this up? So then they came around and said, why do I need 2 people for one job? And so that's how we came. That's how chemical engineering came around. We have one person who can speak chemistry and can do engineering. And I say, and I mean it, speak chemistry. We learn chemistry, and if you are going to pursue chemical engineering, or you're interested in chemical engineering, you will take a lot more chemistry than the other people around. We take a ton of physics anyway, but we also need to take chemistry. So we have a whole year of organic chemistry, we have physical chemistry, you need to take biochemistry. These courses are not necessarily required for you to excel in the actual CBE courses that you'll be taking. They're not actually required for them. But it is required for you to be well-rounded, because when you get out of here, you should be able to, like I say, speak to chemists. You should not be the one synthesizing these things. You should not be coming up with A plus B going to C. But if a chemist comes to you and explains to you, well, I did this, I did this, I did this, and now you have to scale it up, you should be able to understand and converse with that person. And that's the reason that you're learning this here. Okay? So I know a lot of people are scared of chemistry. They think it's hard. But that is kind of like the hurdle we have in the sophomore year, and afterwards you're just doing a lot of physics and engineering. And you do some chemistry, I'm not going to lie. But it's not, chemical engineers are not chemists. It's something that I still tell my mom and she doesn't believe me. So, we're not chemists. You could do chemistry, you could easily transition into chemistry, but you're not a chemist. So that's how that came around. And you can see the first program that offered chemical engineering was UPenn in 1892, and it didn't come to MIT until 1920, so it's less than 100 years ago. So that's fairly new. Oops, kind of hard to see this again. Haber. Anyone know Haber? Anyone? Yeah. Do you know what he did?
He came up with a process to working in Aspirin.
Yes, that's correct. Yes, exactly. And those of you who are interested, if you listen to podcasts and Radio Lab has a wonderful episode on Haber and his life, and I'll mention it briefly about his life. It is interesting. So Franz Haber got the Nobel Prize in chemistry for this. So basically, the idea is that you can synthesize ammonia from air. This is one of the most major breakthroughs we had in the last century, and I'll show you in a graph why. This alone, this new chemical process, is responsible for 4% of the natural gas used annually today. So think of all the things that we use gas for, to make plastics, to drive things around, to roll these things. 4% of all of the natural gas in the world is used just to create ammonia. We really need this. And it's nice and simple. It comes from air. All you need is really air. And then you need some heat, and you don't need to react more things. And I'll show you the reaction here. That's not it. Well, this is it. You take nitrogen and hydrogen, and you mix them together, and you get ammonia. So nitrogen comes from air, and you mix it with some hydrogen gas, and you do all these funky things to it, and eventually comes out as ammonia. Okay? And it allowed the population to go from 1.7 billion back when he was around to more than 7 today. Because now we have enough ammonia to go grow lots of food, and we can feed all people around the world. And that's how that started. And this is a traditional way that a chemical engineer would see a chemical reaction. Okay? So a chemist would say, well, N triple bond N, whatever that is, H, bond H, they break the bonds, they do a funky dance, and they come together and they come up with NH3. And that's how a chemist uses. Okay? As a chemical engineer, I need to understand that. I need to be able to speak with a chemist who figured it out or whatever. But I don't see it that way. I see these things as coming in. These are my raw materials. I need to buy them. Okay? I need to purchase raw materials. I need to put this into some sort of process. Okay? And chemical engineers, a lot of times when you finish your 4 years here, you usually typically be employed in large companies as a process engineer. So there's no job called chemical engineer. I'm a chemical engineer at XYZ. That's not how it works. You could be a process engineer or a product engineer. And this is the process by which H2 and N2 become NH3. And it is up to you to design this process. So it comes into what we have. We have a reactor here, a catalyst beds, and we have a heater. So I got to heat it up, I suppose. And then I'm going to get ammonia as a product here, but I'm not going to convert all of this. So a chemist would tell you, yeah, you're going to get like whatever, 80% conversion. So for me, what that means is that that 20% of it didn't get reacted. So I could reuse this. Why not reuse the stuff why buy more if I still have it? So I can reduce the amount I have for purchasing here because I have stuff that's not being reacted. So I'll keep recycling it. And we'll go into the product here, we'll go into a heat exchanger, and then it will go into a condenser because now it's really hot, I can't use it. With some, it will then condense, and I can, with a refrigerator unit, get my ammonia out. And I can do recycling, and I can do heat exchanging. You can see nothing really complicated here. I have a heat exchanger, and I have a reactor, and that's all. So I have to apply some sort of heat source. I have to cool things down. I have to react them. This is how I view the reaction. I also have to see, as you can see here, when I'm trying to cool things down, I can't just cool them down. I can't let them wait. I can wait a while until it's cool. I can do that. Or I can just make it easier by using cold water from somewhere, and then they would exchange heat. The cold water that I'm using from somewhere is going to get hot, and the stuff that I care about is going to get cold. That's how a heat exchanger goes. And we have a whole course that's just devoted to heat exchangers and how heat exchange works. And we have a whole course that talks about, well, I'm flowing things coming from here, and it goes all the way to the end. How do things flow? There's fluid dynamics. So that's not us only. Mechanical engineers take that too, like I told you. We are the marriage between the two. So we have to worry about that. We also have to worry about things like thermodynamics. So you take courses on that. So you can see it's just basically all the courses that you'll be taking in CBE are for this to work, for you to understand how this would work. Okay? And the main drive, as I'll keep mentioning it, is economics. And you won't see it until if you're in CBE until you see me in the senior year, where we talk about how do we optimize the process so that wherever we're working or whatever we're trying to make, if it's our own product, how do we minimize the amount of money that we have to get in and maximize the profit? Okay, and that goes in with a whole lot of different things. So this is a little aside. Haber process, the same Haber process allowed for the production of mustard gas in World War I. And World War I was known as the first chemical warfare war. It's the first time that people used chemicals to fight. And he was very much a driver for that. And I have here a quote from him. He actually believed that wholeheartedly. And when he came up with the Haber process, he did that for the world. And then during World War I, he was wholly in the service of Germany. Okay, so this is one graph that's I think interesting to show you from an agricultural perspective. This is for developing countries, not for developed countries. So these are places that have not yet industrialized fully. This is the amount of calories that people will be eating, say 1990 all the way to 2050. So this is something that the reason I'm showing this to show you the growth of the agricultural sector and the need for chemical engineers to come up with new fertilizers or with new processes to make these fertilizers cheaper and easier to get, because we will need to feed a lot more people. As places like Africa and South Asia are developing and becoming more industrialized and up to par with everyone else, we will need to provide them with food. There's a lot of money, there's a lot of research, and there's a lot of opportunity going into this. And this is the agribusiness. This is one of several sectors I will show you. Chemical engineers we're fortunate enough that we can adapt to a variety of different services. So this is agricultural. We have a lot of other ones. But the main takeaway, as a chemical engineer graduate, what can you do with this? You can either come up with new things through research and development, or you can take existing technologies like I just showed you, like this thing, and make this cheaper, easier, simpler, better. Optimize this. So those are the two things that you will need to do. So as you can see, in the agribusiness, we will need pesticides, fertilizers, synthetic hormones, any growth agents, any other things that I didn't even think of, lots of different things. Agriculture, it's not just plants. Agriculture is for livestock. Agriculture is for the creation of anything that relies on plant-based or animal-based. So things like paper mills. We need fibers from places that we grow. So that's also part of agriculture. It's not just the traditional thing, I'm going to go grow an apple or a tree or something like that. So these are big, big companies. One of the some of the most profitable companies in the world are Monsanto and Maktashim and BASF, and they completely focus on this kind of stuff. Well, BASF, no, but definitely Monsanto. And they're behind the scenes. You may not even know them, but they're very, very powerful, and they're very, very lucrative to get positions in. All right. Another field, there's a traditional field that actually brought all this, is the oil industry. I will not talk much about the oil industry. This is the only slide I have on it. But chemical engineers traditionally have been employed predominantly by the oil industry. And that they are focused down in the Gulf of Mexico, so Louisiana and Texas. Big oil companies really like chemical engineers, petroleum engineers, and they have a lot of money. And if you look at all those charts for people finishing engineering, the people employed in the petroleum field typically are the ones who will earn the most. And because they have deep pockets and they have a lot of money to spare on that. So, as you can see, 7 of the 10 most profitable companies in the world are in oil. So I'm not going to speak much about that, but the idea here, again, is to try to optimize the process. I can take oil out of the ground, but I can't use it directly. I need to purify that. I need to separate the stuff into, say, methane and ethane and propane and all these different things. So as a chemical engineer, what you do is you design a way for you to separate this stuff and then to transport this from Texas to New York and for people to use that. So that's just one way that ExxonMobil and all the other companies are using chemical engineers. You could also do some research and development. So what are alternate fuels? What can I do with fuels that's not traditionally being done? Can I make more plastics with it? Can I do all these other things? So that's, again, the two things, or research and development or process engineering. And these are some companies, again, they're not local. I will point out when they're local. So you can see, there's a lot of stuff here, but not yet. So polymers, that's another big important thing that I'd like to discuss. So this is another interesting thing that we all take for granted. We all take for granted that we can go to the store and get pineapples, but we also take for granted plastics. Did you know that less than 100 years ago there were no plastics? They just didn't exist. We didn't have plastics. And just look around, I can't think of things that don't have plastic. Everything has reinforced with plastic. Your clothes have plastic. Your food has plastic. We make plastics. It's so cheap. It's so ubiquitous, and it's mind-boggling to think that there was a time before that. So much so that when we divide the world into materials, and so there's metals, there's these natural materials, there's ceramics, and there's polymers. About four classes of materials. So plastics takes up a whole different thing, and they are largely synthetic, but not all. And plastics are polymers. Polymers are large chains, and you've all seen it, I'm sure, in chemistry. So I have some little buddies here, and they all hold hands. It's a little hard to see, but basically they all look the same, and they hold hands, and that's what a polymer chain is. Okay? Not all polymers are synthetic. Can you think of natural polymers that fit this kind of thing? Yeah. Yeah, DNA. Yeah, exactly. And sugars, proteins. DNA are nucleic acids, and a bunch of nucleic acids holding hands, and you can separate them. Complex carbs, you've heard that. If you take complex carbs like whole wheat pasta, and you digest that, it will break into sugars, which is what the main, the repeating units of sugars. They will make up pasta. So these are natural polymers. There's another one, rubber. There's natural rubber that comes from a tree, sort of like maple syrup would come out of a tree. People use that in ancient time to make rubber. And so there are some natural polymers, but they didn't know what it was. And so I'm showing you Herbert Markov. I'm sure you've seen his name around here. He was one of the people that pioneered this study. And the father of polymers was Wallace Carothers, and that was around the 1930s. So up until that point, any polymers that came around, plastics, natural polymers, all these things, they thought of it, funny enough, as a phase of matter. So they thought there was solid, liquid, gas, and this weird thing, polymers. They didn't really know what it was, And it makes sense. I mean, you look at different polymers, they're kind of like, you look at a plastic, say a gum, and if you hold it in place, it will kind of sag like a liquid, but you can kind of hold it and it has hardness to it like a solid. So a lot of these things, like they kind of act as both solids and liquids. So they thought that. They didn't really know, they had no idea that these things have their own nature. And so what happened with that is another thing of resources. And World War II was a main impetus for the birth of polymer chemistry. We relied on rubber, or natural rubber, to make our tires, the United States, by we. And during the war efforts, we were ramping up for war efforts. We realized that we can't rely on that. Natural rubber came from Southeast Asia back then, and still does. And Japan was a main player down there, and Japan and the United States were not real good friends back then, so the United States put a lot of money into researching how to create synthetic rubber, so we don't have to rely on any natural resources. And it wasn't until Wallace Carothers in DuPont, which is a big company, it's down in Delaware, not far from here, in Newark, Delaware, in his lab, Purity Hall, that he came up with a way to make that. Another one of his big things, he came up with neoprene, which you can see here, polyesters, you've all heard, I'm sure, and polyamides, and nylon. Major thing, and to this day, DuPont is very proud of nylon 66. They came up with it, and nylon changed the world. And I'm showing you here some uses for nylon. You can see it here as in airbags. But I'm also showing you here the nylon riots of the 1940s. So in women's fashion back in the 30s, there was stockings was a new thing, and stockings were made with nylon, and it's cheap, it's durable, it's easy to make. And in the 1940s, there was a rationing going around because we needed it for war efforts. And you could see places like department stores would have it. Women would line the street to try to get the little bit that they had so they could purchase it. So it's just an interesting aside again. Polymers are ubiquitous. These things that you see on your products, these recycled things, they denote the type of polymer or plastic that is being used. And I'm showing you some of the uses for, say, number 4, which is low-density polyethylene. And this is high-density polyethylene, and what they're used for. So these are classes of polymers. And this one is kind of worrying, purpling glycol. That's your blueberries and blueberry muffins. Really? So you're eating that because it has a similar mouthfeel and texture to blueberries. So they put that into muffins. But polymers are not just there. They're not just in lots of different foods. You might find it because it gives it a nice texture in your mouth that resembles the natural thing. So is it safe? I don't know. But it is what it is. And so, yeah, so we can recycle in New York City 1, 2, and 5, whatever that is, 5. Okay? Another major thing that we do in design is try to figure out how to recycle the stuff for real. Because did you know that most of the plastics that you throw down in recycling doesn't get recycled? Did you know that? Did you know why? That's one thing. But suppose you toss really clean stuff. Let's say we were all nice and we clean all our plastics, which we don't. Why is it still not getting recycled? Yeah?
Because China refused to recycle it.
There is that too. Because, well, the reason China refuses it is for the same reason I'm trying to get at. Why are we not recycling plastics? Yeah? It's not cost effective, exactly. You know why? Oh, well, no, actually, what it is that making new plastic is cheaper than using old plastic. And plastic, as you recycle it, unlike glass or unlike glass and metal, it degrades. As you recycle it, it degrades in its quality. So you can't use it to the same extent. And also, impurities in it, you have multiple plastics, and it's really hard to separate plastics from one another. You may have 1 and 2 together, and 2 and 5 together, and 2, 5, and banana together. So it's really hard to separate all these things and use that. So and that's why China is refusing to take all the plastics. So up until not so long ago, they took it because they thought they could sell it. Now they have all this plastic all over the world, and they don't know what to do with it. They just tossed it. And you can see there's like sad videos of little kids living in poverty in big fields of plastic because they just tossed it all, and now they don't want to take it. And I understand why. So one major thing that we do in design is try to think of ideas how to recycle this more effectively from a cost perspective, or if we don't do cost effective, what can we do with this? Because it's really becoming a big deal. Not just the impoverished communities in China, but we toss this stuff down the garbage, and it ends up in our oceans. And maybe you don't care about the oceans because you don't live in it, but as it gets degraded with the sun, the fish will eat some of the stuff. And maybe you don't care about the fish because you're not a fish, but some other big fish will eat that fish, and maybe a bird will eat that fish, and that bird will end up on your plate, and then you'll eat that too. So if you're really selfish, it still will get to you. So even the most selfish of people should still think about ways to do this. It really affects all of us. These plastics, we don't know what they do to our health. Like I said, it's only about 8 years old, these ideas of industrial plastics. We don't really know what this stuff does, completely. So these are big chemical companies. Oh, it's hard to see. I have here the Lind Group. They're not local. Evonik, they are local. DuPont is not so far away in Delaware. Dow is in the Midwest, but Dow and DuPont, they bought each other, and then they unbought each other, and they bought each other again, or something like that. I don't know exactly what the deal is. And then Solvay, that is local. These are companies that are researching new methods of creating new plastics, okay? And there's a lot of money going into this kind of field. Less than in the 30s and 40s and 50s when it was a new thing, but still, as you can see, we don't know a lot of stuff about this stuff, so we still are investigating. Okay. This is another big thing, I'm sure you've heard that a bunch. Nanotechnology. These are new materials, the same way that polymers work. We are investigating this new type of field, and chemical engineers are very much interested in this because they can scale things up and learn and use them for others. And as you can see, it's very new. It wasn't until the 1990s and the early 2000s. It's about 20, 30 years old, this stuff. About as old as you are. And so this stuff is very new. We're still learning about this. Nanotechnology is sort of like, well, nanomaterials. The best way I can think of explaining it. You have chemistry on one end that studies small molecular things. So, on the scale of a molecular bond, which is, about 1 times 10 to the negative 10 or 11. Okay? Then you have physics, Newtonian physics. You could physics, you could taking physics. I push something and it goes down. The laws of gravity and all these things that you're learning are affecting it. These things are not affecting atomic things that chemistry is learning, is studying. But physics, the physical laws of the physical universe does affect that. This thing, the nanotechnology, the nanomaterials, they're somewhere in the middle. So physics, the laws of physics stop taking hold around 10 to the minus 7th or 8th. Gravity doesn't have as much of a pull down that scale. And so you get to an area, a gray area of, the nano, which is 10 to the negative 9th, nanometer, so 10 to the negative 9th meter. That's the scale where both physics and chemistry things kind of marry together, and things are acting and behaving a little strangely. And so we're learning this new science as we're using this. So it's very exciting to kind of do research into why this stuff is important, how does this stuff behave, how can I make more of it, how do I understand it better. So there's a lot of exciting research into this fundamental science. But also, from an engineering perspective, what can I do with all this new stuff? What can I do with all, fullerenes and all these wonderful things that these things make? And that's the interest that's why people are so interested in this, because it is new and exciting, and we need expertise from different areas to understand this. As far as chemical engineers are concerned, I'll show you some important applications that we look into. You can look at these, the nanoscale is about the same size of a cell. And cells do behave in the same kind of way that I've just alluded to, somewhere between chemistry and physics. And so I can talk about drug delivery. How do I deliver a drug? So let's say I took a pill and I want to target, say, my liver. How do I make sure it goes to my liver? Well, I can create a vehicle for it, like a little car. And it will drive around and get to where it needs to get to and then unload the drug there. And it won't unload in my stomach, and it won't unload in my intestines. It will go directly to my liver and do its thing. And I can try to design this vehicle. What do I have to put on it? You know, does it need to be an SUV? Does it need to be a 4x4? I can do all these things. And what I mean by that, your body, say for example, your immune system recognizes different things as friendly. So can I put friendly markers on it, and so it won't recognize that as an enemy? Or can I put things on it so that it doesn't dissolve in the stomach acid and things like that? So really customize that vehicle. That's one example. Another one is nanofiltration. As you know, filters, they have filter voids, and they filter things. As the most rudimentary ones in the playground, you put little sieves and you filter things out of the sand. So if I make them smaller and smaller and smaller and smaller, can I get really, really small things out of my water and make it really clean? So nanofiltration is another big thing people are looking into. And nanobots are some. Here's, I'm talking about nanoprocessors, but this is the electronic industry. They're very interested in that as well. Again, the roles of the chemical engineer would be research and development, as I mentioned, and then manufacturing. Here, because it's new, it's also how to characterize this. How do I know what this looks like? Can I develop new ways to study this? So this is pretty ripe with opportunities. Okay. This was a little funny joke, so just a second to kind of read that, but it's true. Pharmaceuticals, major player in it's a major player in chemical engineering as well, and they are located, a lot of them, in northern New Jersey. There's a lot of facilities in northern New Jersey, and a lot of our graduates end up going there. The idea here is a good example of aspirin. Back in the ancient Greece, they realized that if they took willow bark and they exposed it to hot water and they drank it, they had it go away. They didn't know why. They didn't understand the biology or chemistry behind it. They just knew that that would happen. And it wasn't until 1829 that they isolated the actual active ingredient that does that, which is salicylic acid. And it wasn't until around the turn of that last century that Bayer receives patent for making this on a large scale so we can sell it to everyone in the world. So it wasn't just enough, here was enough, I understand salicylic acid is what's causing it, great. Now I want to isolate salicylic acid out of whatever it is, the willow bark. I don't want the other stuff in the willow bark, I only want salicylic acid, I don't want the other junk. So I want to purify that out, take that out, and then I want to use that. So how do I purify that? And how do I make this enough for everyone in the world? Another problem with this, salicylic acid broke into your esophagus. So they had to actually modify that. So they had to employ some chemists to modify what a salicylic acid would. So it still acts the same, but it doesn't burn your esophagus. So that's one thing that would happen, and so Bayer successfully patented it and sold it. It became a big deal, big pharmaceutical, with a facility in New Jersey as well. So this is the way traditionally drugs reach the market. Some people think around what to do, and then it has to go through a whole bunch of different things until it reaches FDA approval. It's fairly long. It takes about 20 years or so to get there, and you could take whole courses on this regulation stuff. In the design class with me, we do go over this for a bit. This would be talk about like who's the regulatory behind that, what are they looking for, these kind of things. So it's important to understand the regulations as well. So as chemical engineers, you will be, if you're interested in this, you could be doing research and development into new drugs and how to deliver them. Or you could do stuff about formulation. How do I scale it up? How to make it stable? How to make sure it doesn't burn the esophagus? All these types of things as far as the industrial scale is concerned. That's what we're specifically interested in. Okay, and these are a bunch of these big companies. And let me see, Sanofi is local, Pfizer is local, not anymore. Bayer is local, Johnson & Johnson is huge in New Jersey. GSK is in Philadelphia. Merck has a facility in New Jersey, and I think Novartis is not far away from here also. The other ones are, a lot of them have facilities in the United States, like Lilly's in Indiana, I think, but they're kind of far away. But there's a lot of stuff here in New Jersey for this, especially Johnson & Johnson. All right. I'll shift gears something, I guess it's, let me see. Yeah, so in the interest of time, this is the last one I'll do. There's other ones. There's also, chemical engineers are also employed by companies like IBM and Intel to help make large-scale circuits and computer parts, because we do some chemical treatments to create these things. So I'm not going to go over that, but that's also something that you may be interested in. IBM up in Albany and Westchester County. Okay, so this is a particular interest of mine because of my previous work. I used to work at Unilever. Anyone know Unilever? Yeah. Like your parents worked there or something? You're so excited. Oh, okay. Good luck. Okay. Yes. So they're big manufacturers of lots of things. So Unilever, if you're not aware of them, if you do a quick Google after class, it's a big U, big blue U. And if you zoom in on that U, which once you see it, you'll recognize that because it's on a bunch of different products that you use. If you zoom in on that U, you will see tiny little logos of their composite companies. So they own a bunch of brands, and that's how they basically hide behind their brands. So they own Lipton, and they own Dove soap and Axe, and they used to own Skippy, and they own a bunch of different things. They're very, very large. And I think I have a picture. I'll show you what they own in a few minutes. And basically, if Dove soap is doing terribly, it's not going to affect Lipton tea because no one associates it to. That's the idea behind it. And they're a large company. So I want to talk to you a bit about soap. Soap is created by taking fats and exposing them to NaOH. And then the fatty acid salt is a surfactant. And a surfactant acts as a thing that likes both oily things and watery things. So it can take stuff off of your skin and that water can't by itself take. So it will dissolve that and will go down the drain because it likes water. That's the simplest thing I can think of describing this. Surfactants are used in other things too. Wherever you're trying to mix oil and water when they don't want to mix. So we use surfactants to do that. So it's not just soap. And we can talk a whole lot about that. So history of personal care. These are some of the early soap manufacturers. Port Sunlight in the United Kingdom. This is, let me see, how this is working well. Yeah, there you go. These are some old ads that they used back, I don't know, 60 years ago, to advertise personal care products. Okay, their idea basically was to educate consumers. And when I worked at Unilever, there was a big thing that they kind of pushed us to do. We need to educate consumers to use our products. So I'll give you a major example of that. Did you know that about 100 years ago, about 120, I don't know exactly when, people didn't use deodorants? You had a smell about you, but nobody cared. Everyone smells. So you want to put some water, whatever. But nobody really had deodorants and didn't exist. Well, personal care companies came around and said, well, we have this new product, and you can be attractive and businesslike and all these things if you use our product, deodorant, and you won't smell anymore. And so much so, they educated the consumers that it became this standard. Now, if you don't use it, you're the pariah, right? You're the one who's looking crazy. You talk about you behind the back, that kind of thing. So they really tried to educate consumers on how to use things. And I'll give you an example of something that I worked on that a bunch of girls in the audience probably know about this. I know when I started researching it, like my sister, my mom, my wife didn't know anything about it, and now they use it. Micellar water, have you heard of that? Yeah. Yeah, biggest scam ever. So micellar water is a makeup remover. And of course they gave this bald guy, be in charge of it at the Unilever, that's what I did. I worked on creation of micellar water for Unilever. It was a product that came out of France, and the French always know what to do, so we should copy them because that's the idea as far as cosmetics go, right? So it's supposed to be a makeup remover. If you look at regular soap, that's about 11 to 12% surfactant. That's the strength of it. Anything stronger is going to irritate you. Anything less than that is not going to do a good job. So micellar water is about 8% water, 1% surfactant, and then some fragrances and things like that. That's it. And it feels good. It feels nice. It feels like water on your skin. You know why? Because it's just water. And it's true. But they educated the consumers. This is great. This is coming out of France. It's a new thing. It's this and that. It's going to feel great on your skin. It's natural. It's got all these things. We put B12 in it. Who cares? It doesn't get absorbed. We've got to put B12 in it. All these things they tell you are great and important, and they put them in, and they educate the consumer to do that. And it's great. It's a marketing thing. It's a marketing-driven field. The other things I showed you are not necessarily marketing-driven. Marketing-driven. They're driven by consumers' needs. I need a new medication because my head hurts. I need, a new computer because I'm trying to get things faster. This is something that they're pushing on us and then we're using it. So these are some examples of personal care products. I'm not going to diss soap completely because soap did stop a lot of epidemics and it's important to use. You should not use soap. But the effect that we need the special soap for our pinky fingers and for our noses, that's ridiculous. Skin is skin is skin is skin. And you can use the same soap everywhere. Okay? Iris Spring on your face feels dry. You know why? Because you have more nerve endings. That dries your skin too. You just don't feel it. So, do you really need a new facial soap? Well, I mean, if you don't need, because you don't know. I remember reading that on the shoes. I didn't know. I just didn't know. I was like, of course you need to use a facial, this and that. You have to. I just didn't know. If you don't use it, it's going to dry your skin. Because you were not educated on that, we just assume that whatever is available is what we need. We don't need it. If you find a soap that's nice and moisturizing for your face, you can use it for your body, you can use it for your hair. It doesn't really matter as long as it works for you. So a lot of this stuff is nonsense. A lot of it is marketing. The marketing ads you see here, these are the modern ones. Similar. A little more PC, but similar. Okay? Still, we're comparing ourselves to monkeys if we're not using this stuff. We're showing you nice white smiley faces, all these things, very much similar to what they had back then. This is what I meant to show you. So, this is Unilever. I'm sure you've seen this if you didn't know before. They own all this stuff. Coca-Cola owns all this stuff. So all these brands that you go to the supermarket to buy are owned by about, 8 to 12 companies, really, behind the scenes. Okay? As a person who goes into personal care or household or food, which is all of these, the science and engineering is the same. You can transition from Coca-Cola to Unilever to Heinz and all these things. And you'd be doing the same kind of stuff. Researching things, if you're interested in that, or scaling things up. If I want to make enough Dove soap for everyone, what do I do? Where do I put this chemical plant to do that? Okay. Let me see. So these are some. We're doing for personal care industry. Yes, this is some of the processes I just mentioned. Okay. Let's see. I have 10 minutes. Okay. Okay, so I want to show you, this is a bit outdated, but not so bad. I want to show you employment of chemical engineers by area, and also how much you could be making. So you can see, traditionally, like I mentioned to you, oil industry will be here. And so you can see a lot of employment is down in the Gulf of Mexico. There was a lot of stuff here in the Northeast and in the Midwest and the Rust Belt, although that's waning. And you can see, like the Rust Belt is not doing well because a lot of the manufacturing was taken out and getting outsourced. And you can see chemical engineers are paid less in the Midwest, $59,000, and much more in the Gulf of Mexico, about $107,000, $144,000, because of the shifting trend. But in our area, it's still pretty good. So in this area, it's still fairly good. A lot of people stay here. A lot of people go down to Texas, but I think most people stay here. So this is our curriculum. So in the first 2 years, as you all would do, you take the fundamental physics and chemistry. I mentioned some of the chemistry that you're taking in the first 2 years. And it's not until the junior year that you start taking the actual courses that are, well, that you need to study all these things I mentioned. So, transport phenomena, that's how fluid mechanics, this is this. Heat transfer, I mentioned before. We have to learn how things exchange temperatures. And what do I do with all this hot water that I created? Do I just dump it down the ocean? Or is that going to kill fish? And mass transfer, that's how do the higher concentrations move to lower concentrations and why, and can I use it to my advantage? We talk about separations in a whole course. How do we separate things? So you might think to yourselves, I can easily separate things. If I have a mixture of something, I can just separate it with like a filter or something like that. Sometimes it's not so easy to filter. So here's an example. Water and ethanol. You're trying to create high percentage alcoholic drink. What do? Well, you might think I'll heat it up. So I'll heat it up and I'll heat it up and heat it up. And the ethanol has a lower boiling point than water. Ethanol is 78 and water is 100 degrees Celsius. So you might think, yeah, well that makes sense. I'll just boil the water, all the ethanol, collect it, and I'll have ethanol. But the thing that happens is that at some point there's a thing called azeotropic point, where the boiling point of the two coincide. So at a certain concentration, boiling point, which is dependent on concentration, they will coincide. And at some point, when you heat it up, you will get rid of both ethanol and water at the same time. So you're not going to be able to purify that. You cannot collect all the ethanol out of a water-ethanol mixture. So what do you do? So what's that? There are different technologies, like, well, there's distillation, you've heard of that, but there's other technologies you could use. You could say freeze, dry things, you can just freeze the ethanol out and take it out. You can add impurities to it. You could use some of the more radical separation things. So you could use membranes to your advantage. You could use bioorganisms as well. Not just ethanol water, but this is the type of things that we study in separations. How do we separate things from new technology to old technology? And how do we do that without breaking the bank? And then reaction engineering. This is to study what do I do with a chemical reaction? How do I scale it up? What happens if I put that into a reactor? What kind of reactors are there? What do reactors do? So sort of like an equipment type thing, not the chemistry point of it, but the equipment of it. And how do I use that to my advantage to carry out what I need? Unit operations, this is our senior lab. So like I mentioned, so let's have a separation unit, like distillation. You're going to be interfaced with a big distillation tower in the lab, and you're going to play around with it and study how it works. And what happens if I flow things through it, or if I heat it up, or if I cool it down. All these things, and you start learning about the parameters behind that. Or you look at a reactor. What's a reactor do? How do I play with a reactor? Okay? And this is my course, Process Synthesis and Design. This is what is called the capstone course. Capstone, if you look at an arch, is the top stone that holds the whole arch together. If you take it out, the whole thing falls apart. And the reason it's called that is because it takes all the stuff you learn in chemistry, physics, and engineering, and you're going to do a big design project throughout the whole year, and you're going to be learning about things like economics, about things like rigorous scientific vetting of a process, but also you're going to be learning things about the current state of affairs. What do politics and politicians and what does society say about a certain thing? What do we need? Is there a need for something? Are we trying to get somewhere? So, for example, there's a lot of push for, say, cleaning waters, and how do we clean water, or how do we recycle plastics, or how do we all these different things that are pushed by society, rightfully so. How do we do that, and where are they coming from, and how can I use it to my advantage in new ventures, new entrepreneurial ventures? We also look into things like environment, safety, and health, and also ethics. Anything that's unethical, you should be able to flag it and say, well, I mean, legally I can do that, but should I do that? Right? I mean, there are regulations in the United States. If I cannot dump hot water from a process into a river. It will kill fish. But if I go and I do it in, say, Afghanistan, there are no regulations, but it's not ethical. Should you do that? And what does it look like to consumers? Okay? So we study all these things. And we also have material science. This is an example of a plant design that we did 2 or 3 years ago. the Haber process, and we studied another method of doing the Haber process, and we optimized this thing here. As you can see, nitrogen and hydrogen come in, they go through a compression cycle, they have a heat exchanger, they have a reactor. They again do, after they reacted, we're trying to pull it down, and then we need to separate the stuff. We separate the stuff into ammonia, and then stuff we can't use, we take out, and this stuff we can use, we bring back in as a recycle. And so on and so forth. These are the unit operations I mentioned. I think I'll just skip that. And I think nothing else now. Here. Yeah. So yeah, thank you.
One last comment for this semester. Keep in mind on the EG website, if you go to the lecture tab, you can download all of the lectures. The previous 2 weeks, the World Trade Center and the robotics lecture are not posted due to the content that was included in them. However, we'll have this one posted up later on this afternoon, so please take a look at those. Good luck the rest of the semester with your projects and with the rest of the
So next week I won't be able to meet, but the following week.
Thank you very much. Why 37 at NYU?
Yes, that's right. Okay.
Yeah, and I have two quick questions. So, what's your suggestion for
To take in, well, if you, what are you a great course, I mean, we don't require the
Just a quick comment, just in case you're not sure with SUE has a lot of flexibility. What I would do is, until you're certain you want to switch over, or are you certain already? Okay. Go to NYU Tandon's website, go to chemical engineering, look at the common curriculum, and it has the first year courses that you should take. So enroll in all of those courses. Make sure you get all of those in because they're all prerequisites for the second semester. And based on what you had this semester, you might need to take a class or two a little somewhere if it's possible, but I would also talk to your advisor.
Right. Do you take Gen Chem now?
no, I have
Oh, okay, so, okay. And
You're
then,
good.
Matt, are you where are you with Matt? It's in Cal 1?
I have AP. Oh, so you have, okay,
So you're set because you have a lot of AP credits, so you're probably flexible. You can probably get back in track just setting up the right courses for the spring. Have you enrolled yet?
No. I'm kind of want to talk to
Okay.
maybe you want to shoot me an email and I'll let you know kind of like what to expect, because I'm also invited. Okay. YM 37. Yeah. Thank you.
I think you'll really enjoy it.
Yeah.
Yeah.
Thank you. Oh, okay, sure. Thank you.
Thank you.
Thank you.
But, kind of like general question is like, how do you think like, journalism of like science books, I know some people like references that.
Yeah, well, like in a place like Unilever, they kind of drive that.
Yeah, so like, how much of like scientific discovery just actually like stumbling upon things or is like,
Well, they restrict you. So, like, if you go into like a more pure or R&D, which is grad school or academia, you're more open to things. Not as much as you'd like, but much more open to things than you would be in industry. So, in industry, they tell you cannot study this. Like, you're on this line. You gotta get this stuff. But look, I found this new method of doing this and that. I don't care. Do this and this and this. So you can't do that in industrial process. Usually, some places are more flexible, but most that I've seen are not.
so I can be a math scientist?
You could be a mad scientist if you kind of run your own lab, or if you start your own company. But if you're running a lab, like say, the professors are mad scientists in a way too, because they run their own labs at schools, and then they can come up with different things for projects, and it's up to them to come up with these ideas. And they are driven by what's needed out there, but they are much more flexibility.
That makes
But I have a question about the academic route. I don't want to go academic route, like professors, like research assistant, like do you like research as a professor, like do you like really specialize as a professor, or is it like more like broad range?
So at the end of the 4 years, you have basically the option of, well, you have three options. You either go into industrial engineering, whatever your field is, you go into academic engineering, it's grad school, or you don't do engineering, something else. So if you go into graduate school and you go into your PhD, usually you have a project that you work on and specialize in 5 years or something like that. And that kind of sets you into some sort of niche area, but that doesn't restrict you into some place.
Yeah.
So mine was in nanotechnology and polymers, but I ended up at Unilever. And actually got interviewed by IBM. So that doesn't really restrict you to one area. But once you start somewhere industrially, usually you tend to stay in that area because that's your expertise. But if you want to do professorship, after your 4 or 5 years of a PhD, usually you go for a postdoc or something like that, and it's like a year or two of research in someone else's lab. It's like an additional PhD without a degree. And then you go and you get a position as a professor in one of the schools around. And over there you also have two options. You could go the route I chose, which is more teaching professorship, or you could do a research professorship, in which case you are more of a research professor, and then you don't teach as much, but you do a lot of research. You have your own lab, and you're running your own lab, and you have people working for you, and you're getting their own PhDs. And you have undergrads and master's students also helping out.
Okay.
Does that make sense?
Yeah.
It's like a very broad.
Yeah. That's not bad at all. It's not bad at all. Just talking about PhD program like that. Like,